Let's talk about optimization. Optimization is where you have to find some kind of maximum or minimum in a situation that's subject to a constraint. Optimization problems will always have two things, a constraint and a goal. A constraint is something that needs to be true throughout the whole problem, while your goal is what you're trying to maximize or minimize. An example of an optimization problem is finding the area of a fenced-in region. Your constraint in this case is the amount of fencing you have available to you, whereas your goal is to maximize the amount of area you cover. Another example of optimization is constructing a box, where the constraint is the specific dimensions that you need to build the box to, and your goal is to minimize the cost. When dealing with optimization problems, it's important to remember your first derivative rules. Zeros are the first derivative will possibly be maximums and minimums of your function, so that can be useful when trying to solve optimization problems. The first example we're going to look at here is finding the area of a three-sided fenced-in region. We're going to try to build a region shaped like this rectangular region with one side already taken, only using 43 yards of fence. We're going to try to maximize the area. So in this case, as I mentioned earlier, our constraint is going to be the amount of fencing we have. The length of these two sides, plus the length of this one side, cannot be larger than 43 yards. If they were smaller, we would not have a maximized area. So we set this equality up as our constraint. Our goal is to maximize the area, which in a rectangle is going to be this length times this width. So here we have this expression, a equals xy. Now we know that for a maximum or minimum, we're going to want to take the first derivative and set it equal to 0. But right now we don't really have any way to do that because this function has more than two variables, and it has a, x, and y. So what we're going to do is we're going to use our constraint to write an expression for y in terms of x, which we can then substitute back into our area formula, and then get an expression for area in terms of only x. Now we can take the derivative with respect to x to get that dA dx equals 43 minus 4x. Notice how here we distributed this x to this term that we substituted in for y. We could have done a product rule if we wanted to, but I usually find it easier to distribute and then do multiple power rules. Since we know that we can find our maximums and minimums when our derivative is equal to 0, we can set dA dx equal to 0 and solve for x to find that x would be 4/4. Our next step is to determine whether or not this point is truly a maximum or not. There's two ways to do this. The first is to take that value in the first derivative and plug in values smaller and larger than it to see if our function has positive or negative outputs. Here we find that for values smaller than it, such as 0, our function has positive outputs, and for values larger than it, such as 100, we have negative outputs. This means that our function is going from increasing to decreasing, meaning we have a local maximum. The second way to do it is the second derivative test, where we take this first derivative, derive it again, and we see that we get -4 as a constant answer. This means that our function is perpetually concave down, which means that at the point 43/3 we have a local maximum because the first derivative is 0 and the second derivative is negative. Now knowing the value of our x length, we can plug that back into the y equation we found earlier in order to get the second dimension, and we get the dimensions of our rectangular fenced-in area should be 43/4 by 43/2. Our second example is going to be optimizing a product. So we're given that we have two numbers, a and c, that need to sum together to equal 437. That's going to be our constraint. And our goal is going to be to maximize their product, which is a times c. So here we have this expression written, p equals a times c. You'll notice this looks very similar to the previous problem we just did, so we're going to solve it the same way. By solving for a in terms of c, we can then plug that value back into our product to get an expression for p in terms of only one variable. Then after distributing to get a more simplified equation and taking the derivative, we can then set that equal to 0 to solve for c. I'll pause for a moment so you can take a look at this math. Our final example is going to be a little bit more complicated. Like I mentioned in my overview earlier, one of the possible situations we can use optimization is constructing a box to meet certain specifications while minimizing cost. So we're going to build a box to certain specifications. The length of the box has to be 3 times the width of the box, and the total volume has to be 50 feet cubed. We also know that our sides, the cost of the material used to make the sides of the box is going to be $6 per square foot, and the cost to make the top and the bottom of the box will be $10 per square foot. Our goal here is to minimize the cost, and our primary constraints are this volume restriction and this expression here, which we can use later. So first we should write our constraint, which is that our length times our width times our height equals 50, and then by substituting that length in for 3 times the width, we can get an expression for our constraint in terms of our width and height. We can then write the goal equation for our box here, which is that this front side, which is going to be the length times the height, and this side, which is going to be the width times the height, are going to cost $6 per square foot of their area, which is calculated with these expressions here. And we'll have 2 sets because of the front and the back, and the right side and the left side. We calculate the cost of our top by multiplying our length times our width, multiplying by 10 for the cost, and by 2 because we have a top and a bottom. And by summing both of these major terms, we get C, our total cost. Now, what we can do is substitute in our L for 3W like we did in the previous equation to get this more simplified expression in terms of W and H. And finally, what we can do is by taking our initial constraint here and solving for H, we can then get an expression to plug back into this equation in order to reduce our equation to just the variables C for cost and W. This will allow us to later take the derivative of C with respect to W. This next step here is a little bit of simplification to make our problem look nicer. Our next step is to take this equation and derive it with respect to W. You'll notice here I distribute this 12 to both of these terms in order to get something that's a little bit easier to derive. Once we've derived this expression, we'll get 120W plus negative 200 over W squared plus negative 600 over W squared is equal to our dC by dW. Combining like terms for these two, we'll get negative 800 over W squared plus 120W equals 0, because we know that we need to set our derivative equal to 0. Solving for W through a couple of arithmetic steps here, we can get that W is equal to the cube root of 20 over 3. Knowing that length has to be 3 times our width allows us to easily find length as 3 times the cube root of 20 over 3. And knowing that our height has to be 50 over 3W squared allows us to find that our total height is 50 thirds times 20 thirds to the negative 2 thirds. And that is how we find the dimensions of that box using optimization.